Okay, let's continue looking at the structure of the atom subtopic in the light and atoms topic. And in this final episode, we're going to look at lasers, or how lasers work. And in particular, we're going to look at the concept of stimulated emission, which is basically the principle on which lasers work. Let's get into it. Okay, I am competing with a bit of background noise today, but hopefully this turns out okay. So let's look at the processes of, we'll briefly recap the process of absorption and ordinary or spontaneous emission, and compare that with stimulated emission, which is really what you need to be able to do. So let's start out here with absorption. When a photon with energy corresponding to a transition from a higher energy state to a lower energy state is incident on an atom in the lower state, it can be absorbed by the atom. What does that mean? That means if we have light coming in towards an atom and that light has energy that corresponds to an energy gap between two levels in the atom, E2 minus E1 is basically that energy gap, then that photon of light can be absorbed and put that atom into a higher energy state. We looked at absorption spectrum in the last episode, and hopefully that's just a fairly simple example of that. Remember, these were like the steps on the ladder. It can only absorb light if it corresponds to the energy level gap. So that's normal, simple absorption. Now, what normally happens following absorption is that if the atom is in the higher energy state, it will relax back to the lower energy state, and when it does that, it will release a photon that corresponds to that energy level gap. So we've looked at that before in terms of emission spectrum, emission spectroscopy, and also fluorescence is related to that idea as well. So we call this ordinary or spontaneous emission. Now, the next type of emission is a little bit special and leads to some really special consequences. When a photon with energy corresponding to a transition from a higher energy state to a lower energy state is incident on an atom in the higher state, it can stimulate the transition to the lower state. So if we have an atom in an excited state, like we did here with ordinary emission, but rather than it just undergoing spontaneous emission, if a light is incident on that corresponds to this energy level gap, it will stimulate the atom to relax, and when it does, it will produce two photons. And those photons will have some very special properties, and we'll talk about that on the next slide. So those photons that are emitted in stimulated emission will be identical. And when we say identical, they will have identical energy. Therefore, they'll have identical energy, they'll have identical frequency, E equals HF. Because they have identical energy and or frequency, they'll have identical wavelength, E equals hc on lambda. And they will also be travelling in the identical direction, and they will also be in phase. So if you can remember back to the interference of light topic, that basically means when one has a peak, the other has a peak. When the other has a trough, the other has a trough. They're monochromatic because they have the same wavelength and the same frequency, but they have that constant phase relationship as well. So we say that that light is coherent light. Remember, we needed coherent light to produce interference patterns. So that is what is special about the photons produced in stimulated emission. Now, you might already be thinking, oh, that's how a laser works. A laser has light that is coherent. It has light that is high intensity. It has light that is all travelling in the same direction. And you'd be correct. So, what do we need to make a laser? Well, firstly, we need this stimulated emission, but we need something else. We need something called a population inversion. A population inversion is produced in a set of atoms whenever there are more atoms in a higher energy state than in a lower energy state. So if we consider here now, and let's just assume this diagram represents 4 atoms, if these atoms are all in the low energy state, so that they're all in the more relaxed form, when light comes in here, it is more likely to cause absorption to the higher energy state, but we are not going to be producing this stimulated emission because we haven't got atoms in that high energy state. But if we can create a lot of atoms being in a higher energy state, like in this diagram here, so when we have more in the high energy state than the low energy state, that's what we call a population inversion. And now, if we put light onto that, we will get all these stimulated emissions that will release 2 identical photons. And each time you get a stimulated emission, we'll get the release of 2 identical photons. If you like, the emitted photon will be identical in terms of frequency, wavelength, direction, phase relationship to the incident photon that comes in. So, we know about stimulated emission. We know what a population inversion is, more in the excited state. How do we create a situation where we have this population inversion? And to do that, we need to use, well, let's read what we've got here. Some excited states last for a relatively long time before the atom undergoes a transition to a lower energy state by spontaneously emitting a photon. These states are called metastable states. So, I talked in the fluorescence video about very long-lasting excited states leading to things like luminescent and things that glow in the dark. Well, metastable states are a little bit like that. They don't need to last for, minutes and hours, but they will last for relatively long times in terms of physics. If we have an atom with a metastable state, that basically means that we can set up a situation where we get more stimulated emissions than absorptions, so we can basically set up the conditions needed to produce laser light. For practical systems, the high energy state must be metastable if a population inversion is to be produced. So basically that's just saying you've got to have this metastable state to set up this population inversion to make a practical laser system. Now, the next thing we just need to quickly talk about, describe the useful properties of laser light. Now, I think I've already probably covered that, and just to even make it easier, even in the curriculum state, they cover it afterwards. And it says here that they're coherent, monochromatic, and high intensity. That's what makes laser light so useful. The fact that coherent, which means it is monochromatic, and also has a constant phase relationship, all travels in the same direction, so we could say unidirectional or something like that as well, but same direction. And because it's all travelling in that one direction, it is very high intensity. That does lead to some dangers. So we're going to discuss the requirements for the safe handling of lasers. Laser light is very high intensity. It can damage sensitive tissue, like your eyes, but other sensitive tissue as well. So it's really important when using lasers that you have proper eye protection that can stop that high intensity radiation damaging your eyes. And you also basically need to, wherever you have that laser going, have it reasonably well shielded, and it needs to be shielded in a non-reflective way, because if it's shielded with something reflective, that laser light can potentially bounce off it. That light can then bounce off, and you may not know which direction it's going to bounce in, and before you know it, it's bouncing into someone's eyes, and we don't want anyone to go blind from getting accidental laser to the eyes. They do actually use lasers for eye surgery. It is how they basically reshape your eyeball when you have certain conditions. I think they also use it to remove cataracts and things like that because of its high intensity. But apart from those scenarios, you generally don't want to get laser light in your eyes. It won't be very good for them. So that wraps up the structure of the atom topic. Next, we will get into the standard model.